Okay, so here we're going to be doing a polyprotic acid and we're solving for a variable. Specifically, they're asking us for the equilibrium molarity of HPO4 2 minus. Now, one of the things that you, if you watch the previous videos on polyprotic acids, if they give us the initial concentration of a polyprotic acid and they give us the Ka for the first step, we can figure out the H plus concentration from the first step, and then that is the pH. We can take the pH from that for the entire step because so much more H plus is produced in the first step than any others. And if you take a look, I borrowed this from the ALEKS bank here. If you take a look, what they're asking us to solve for is they're asking us to solve for this. But what they're giving us this amount of this guy right here. So what are we going to have to do? We're going to have to go from this guy over to these two guys right here. And this is what's really going to be important here. This H2PO4 we can clearly see is also right here. But then what we note is that this H plus amount here, it's going to stay in the solution the entire time. And the amount of H plus that's generated additionally from here and here is so small compared to the original amount of H plus generated here that we don't have to worry about adding the amounts in from each of these two steps. The other thing I want to point out to you here is that the College Board, do you notice how the very first step here, they give us a Ka of times 10 to the negative 3? And when you have a Ka that's that big, I use that term tongue in cheek, you can't use the 5% rule. So we're going to, unfortunately, in this problem, have to use the quadratic formula. But in the College Board, they'll probably invent some H3XO4, and they'll make believe what the particular acid is because they're never going to require you to use the quadratic formula. But let's move forward and see what we're going to do right here. Again, we know what our Ka value is. We can write a equilibrium expression or law of mass action from that. And if we did that, we'd end up with our K is equal to, remember, it's the products raised to their coefficients all over the reactants, right? So we're going to go H3O plus times H2PO4 minus. And since the coefficients are all ones, makes it a pretty straightforward problem. And on the bottom, we're going to have H3PO4. Do we include this pesky little H2O in any of these circumstances here? No, and quite simply, it's because it's a liquid, and we don't care about liquids. We're a little bit ugly that way. Now, if we actually were to set this up in an ice problem, I'm going to move this over a little bit here to the side so we have a little more room. I'll put this over here, right? And in fact, I'm going to cover this bottom one because we don't really care about it. But if we were to take this first step right here and we were to make it H3PO4, I'm going to ignore the water right now because I want to make it a little bit smaller. And that's going to go to H3O plus plus H2PO4 minus. Again, it seems sort of weird to not have the H2O in here, but just realize it is right here. But if I do an ice problem for this, I'm going to start off with 0.22 molar, right? And that's going to go right here, 0.22 molar. I'm going to start off with 0 and 0 this, which means that the only way our reaction can go is this way, which means that we're going to be subtracting from this side and we're going to be adding over on this side. When we set it up, we're going to go minus x here, plus x, and plus x, and we'd end up with 0.22 molar. Again, we don't write the m in here because that makes it kind of a pain to it doesn't really cancel out very well. And then we have x and we have x. And we would think that if we're plugging it back into this equation right here, we think we'd be home free because that looks an awful lot like our typical dead frog expression. X and x go into here, and then on the bottom we have 0.22 minus x, but here's the thing, and that's all equal to this value right here, 6.9 times 10 to the negative 3. This is the problem. We cannot cancel this out. So what that leads us to is if we take this right here and multiply it over here, we're going to end up with a polynomial that we can then plug into the quadratic formula. So if I were to set this up, I would write it out like this. I'd end up with x squared is equal to Let me just write it all the way out here. 6.918 times 10 to the negative 3, all times 0.22 minus x. And then when I distribute it out, I end up with x squared is equal to 0.006918x minus 1.522 times 10 to the negative 3. So we have our A, B, and C expressions. And when we solve for x using our equation, we end up with negative 0.006918 plus or minus, this is all, and you guys probably have sang the song before, I'm not going to sing it, 0.006918 all squared plus 4 AC, right? 1.522 times 10 to the negative 3, and all of that is over 2. And when we solve for this, we end up with two values for x, as we always do, and it's going to be 0.03571, or we're going to end up with x is equal to negative 0.04262. And we know this to be true. We cannot have a negative molarity, so that means that this is the molarity that we have for our x. Now, what is really important is that this x value here is equal to two things. It's equal to our H3O plus concentration, and it's equal to our H2PO4 minus concentrations. So if we go back up to here, we have just solved for these two values right here. And why is that important? Because ultimately in the problem, they're wanting us to solve for the concentration of this. So what that means is we're going to then use this equation right here, but we're going to start off with this and this in these two places right here and right here. So if that's a little bit confusing, let's rewrite, but this time we're going to write it with our second equilibrium expression, and it's going to be our H2PO4 minus plus water. This is aqueous. This is a liquid, as always. And we're going to end up with H3O plus HPO4 2 minus. And remember, this is what we are looking for. We're trying to solve for the concentration of that. So what are our starting values here for our ice problem? Well, in this ice problem right here, we have to go back and we have to take a look at what they gave us in what we solved for right here. This right here and this actually not this right here. This right here is equal to our H3O plus concentration and our H2PO4 concentration. So that means that this is our starting value right here. So we're going to write 0.03571. But it's not just our starting value for this, it's also our starting value for our H3O plus, because remember, x is equal to, and I didn't put a parenthesis around this, but from the previous problem, it's equal to both H3O plus and H2PO4 minus. So we're going to have 0.03571 here, and here we start off with our 0. Now, again, as is always the case, we're going to go minus x here, we're going to go plus x here, and we're going to go plus x here, and then we have 0.03571 minus x, 0.03571 plus x, and we have x. Now, if you take a look at this equation up here, this second one right now, if we were to write the k expression for it, and we wrote it to this one right here, I'm going to write it down below because this is the k that we're going to be using. We're going to write Ka, and we're going to call this Ka2 because the first step over here, and just to keep track of it, Ka2, Ka3, this keeps track of Ks when there's more than one dissociation in a problem. That's going to be equal to our H3O plus times our HPO4 2 minus all over our H2PO4 minus. Now, the really, really good news in this is that the K value for this is incredibly small. It's 6.166 times 10 to the negative 8. And why is that really good for us? Well, if it's 6.166 times 10 to the negative 8, that means that we can use the 5% rule. So let's plug in our values, these values right here. These two are going to go, this is going to go here, this is going to go right here, and this is going to go right here. So when we plug them in, we now have this. Ka2 is equal to 0.03571 minus x times x all over 0.03571 plus, sorry, I did a minus x here, but I really meant to do is a plus x here. Sorry if that confused you. Minus x, I'm not going to bother going back and fixing that, is equal to 6.166 times 10 to the negative 8. And here's the beauty of this. Both of these here, if we compare them to our original values, this x right here compared to this, and this x compared to this, they are negligible. They're less than 5%. So what we can do is we can 5% rule this, and we can 5% rule this. And if you take a look, it makes a really, really simple problem, because what do we have left on the top? We have 0.3571 and 0.3571, which are the same value, which means that we can cancel these guys out. So what does that leave us with on the top? X is equal to 6.166 times 10 to the negative 8. And what is x equal to in this case? Well, let's take a look. Didn't we say that x was equal to HPO4 2 minus? So in this particular problem, this is equal to our HPO4 2 minus concentration, and that's our solve. Now, they ask us in this particular problem to do it to two significant figures. In reality, if we look back at the original problem, they give us two significant figures, so it makes sense that we do it like that. So we're going to go back down here, and if we're doing it just to two significant figures, wouldn't these two be the only numbers that we're going to use? But wouldn't this 6 round this up? So our final answer is going to end up being 6.2 times 10 to the negative 8 is equal to our HPO4 2 minus concentration. Hopefully this has been helpful. We'll see you again soon.